The second derivative and concavity. Consider the graph of y is x cubed minus 2x squared minus 5x plus 6 below. So we can see the shape of the graph, and we can see a point of inflection indicated on the graph just here. Now, this is different to points of inflection you've met before. You've met the horizontal point of inflection where the gradient goes 0 just at some point in the middle. This is an oblique point of inflection. So an opoint, oblique point of inflection. And what an oblique point of inflection is along a section of graph, the curve gets shallower for a moment and then goes steeper. And the minimum gradient along there is an oblique point of inflection. Or what you have is a shallow piece of graph that suddenly gets steeper and then shallower again, and the steepest point is an oblique point of inflection. And indeed, that is the case here, because we can see that we have a turning point here, and therefore the gradient is 0 here and here, so the gradient is 0. So from this turning point at the top, the graph comes down, getting steeper, 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 but then it has to start getting shallower again to go in towards the other turning point. The point where the gradient is maximized is that oblique point of inflection. The curve is concave down to the left of the point of inflection. So we can see the shape to the left of the point of inflection. The graph is concave down. It's concave up to the right of the point of inflection. So we can see that if we go to the right of the point of inflection, it is concave up. It is easy to remember which one is up. Remember, it is U-shaped. We talked about this before. Compare this with the values in Table 2 in the example above, or table in example 2 above, which was this table just here. The point of inflection is at 0.67. So these points here are all to the left of that point of inflection. And the second derivative is negative at those points. So it seems that a negative second derivative indicates concave down. If we look to the right of the point of inflection, these are all positive. So positive is concave up. Now remember, if you're feeling positive, you're feeling up. It should be easy to remember. So let's just bring the table out of there again. And we're going to reiterate those points. So d2y dx squared is negative at the x values where the curve is concave down. d2y dx squared is positive at the x values where the curve is concave up. d2y dx squared is 0 when the curve is neither concave up nor concave down. At a point of inflection, although you have to be careful with that, there is a note just here. Be careful with this. The second derivative is always 0 at a point of inflection, but we cannot use it to identify a horizontal point of inflection, as it is possible for the second derivative to be 0 at a maximum or a minimum. And we'll see an example of this later. It's just a case where you need to take care. But this does have implications for finding maxima and minima. So if we know the curve is concave down, so it's that shape, if we have a turning point on that section, it should be a maximum. And if a curve is concave up along a section and we have a turning point, then that should be a local minimum.